Talking chapter two. So we did a little bit yesterday as well. So yesterday we talked about a couple important things, the rules to follow when you're trying to identify something as a significant figure or not. So remember that in terms of significant figures, any non-zero is significant. So again, we always start counting really left to right on a number. We really do not start counting significant figures until we hit the very first non-zero. And at that point, that's where we're going to really start counting. We had a few different types of zeros that we talked about. And there are leading zeros that are not significant. And those are all the zeros that come before, again, the very first non-zero. So again, all those zeros there that are underlined would not be significant because we have not really started counting our significant figures until we hit the 3 in this case. And then obviously the rest of these would be significant. So this would be 3 significant figures. There's also the trapped zeros, the captive zeros, and those are significant. And those are, again, zeros that are between two non-zero numbers. So since we are counting our significant figures there, and this guy is significant, those zeros in the middle would be significant. And again, it would have 4 significant figures. And then probably, again, the sort of zero that gives most people trouble is that trailing zero. And that's the zero at the end of a number. And what gives people trouble with that, again, is it can or may not be significant. And what determines whether or not it is significant is there a decimal point in the number? And in the case of sort of counting significant figures and those zeros, this is not a imaginary zero decimal point, not imaginary decimal point. It actually has to be written in a number. So you can't just assume that there should be one there. It does have to be actually written in a number for those zeros to be significant. As we also saw in that weird example I did with 11 significant figures or 12, however many that one had, the decimal point does not need to be near the zeros. It just needs to be anywhere in the number for those zeros at the end to be significant. We also talked about, obviously, with scientific notation that all those numbers, again, before the times 10 part of a number is significant. And we talked about, again, that you could kind of really dial in your significant figures if you write a number of scientific notation. You can almost control how many that you put there. We talked about as well exact numbers. And remember that exact numbers are basically found one of two ways. It is either something that you just simply count. So you're not going to do any type of like measurement to figure out how many you had, like, again, how many pens you have on the table or something like that. You're just going to simply count them. The other one are definitions. And as we saw, there's a few definitions that are considered exact numbers. And those are, again, pretty much any equality or sort of conversion that is an English to English conversion, or anyone that definitely is a metric to metric conversion. Those guys are going to be considered exact numbers. When you typically cross over, though, and convert from, say, an English unit to a metric or a metric back to an English unit, those usually are not considered exact numbers. But there are a couple that are. For example, there's a couple on that little list, I think, on that slide, like 1 inch is 2.54 centimeters exactly. 1 pound is 453.6 grams. So those are considered exact numbers, even though there are crossing over. But a vast majority of the ones where we cross over from metric to English are not considered exact numbers. What is the deal with exact numbers, as we'll talk a little bit more about today as well? They basically can have as many significant figures as you like. And the real result of that is, and sort of how you're going to use them, is you really do not need to worry about exact numbers when you're doing calculations in terms of your answer and how many significant figures your answer should be. So if you come across something that is considered an exact number, it's actually a good thing. You kind of ignore any contribution it may have to your answer in terms of significant figures. I think the last thing we covered yesterday was rounding. And again, we don't want to do any extreme rounding. We just want to follow normal rounding rules. Less than 4, obviously, we usually drop the numbers, right? And above 5 there, or 5 and above, we kind of round up. Any questions on any of that stuff there? Okay. All right, so obviously here, if we're going to 2 significant figures, and we look at this number, this is going to be our second significant figure going left to right. We would then need to look at the next number, which is a 7. That is above 5. And once again, we would need to round it up to 36 in this case. Taking a look at the next one, our second significant figure is right there. We would look at the next number, which is a 2. That means we typically will drop the numbers. Once again, as we talked about yesterday, although you could write 38 grams, and that is 2 significant figures, that definitely is not the same meaning as the original number. So again, as we were just talking about, you do not want to do any extreme rounding like that. So in this case, we actually do need to put some zeros in there so that the number maintains really the value it should be at 3,800 versus 3,826. Could I do 3800 with a decimal point? I could, but it definitely would not be 2 significant figures at that point. Again, by putting the decimal point at the end, that would cause those last zeros or trailing zeros to be significant, and we would have too many significant figures in that case. Coming over here, remember, we do not start counting until we hit the first non-zero going left to right, and that is the 2. Then the 6 is where we want to stop. We take a look at the 2 in this case, and here we do just drop the rest of the numbers to get us to 0.0026. Once again, if you just did this, although the number here is okay in terms of the meaning, we now do not have 2 significant figures, right? We now have 4, right? So again, we do want to watch out on those. Sometimes we don't want to leave the zeros, and sometimes we do need to add the zeros, just to maintain the right number. Here, if we take a look, we got to the 2, going to look at the 8, we're going to round up, and that's going to get us a 1.3 kilograms. Any questions on any of that there? So then let's talk about when we do calculations, how do we know what our answer should be at the end? And excuse me 1 second here. So when we do calculations, we want to look at the 2 main types of calculations that we do. We oftentimes will either multiply and divide, or we will add and subtract. So multiplying and dividing, or adding and subtracting. We do actually do different things depending on that situation. So for multiplying and dividing, our answer should have the same sig figs as the number with the least number of significant figures. So if you're multiplying or you're dividing, whichever number in that calculation that has the least number of significant figures is really what your answer should be in terms of significant figures. So if I took 1.42 and times it by 2.3, and on my calculator, if I do that, 1.42 times 2.3, we will get 3.266. Since we are multiplying, we're going to look at significant figures. This number here has 3 significant figures. This number here has 2 significant figures. So our answer should end up with the same number of significant figures as the one with the least, and that is 2 in this case. That would take us to this 2 right here, and we would look at the 6, and in this case, we would need to round up, and we would end up with 3.3 as our answer in this case. So multiplying or dividing, no matter how many numbers you're multiplying or dividing, it is whichever one is the lowest number of significant figures, and that is how many significant figures your answer should have. Now, when we add or subtract, it is different in a sense. It is still going to be actually the lowest number, but we are not looking at significant figures here. We're actually looking at the smallest number of decimal places. So for adding and subtraction, we look at decimal places. For multiplying and dividing, we look at significant figures. So adding and subtraction, your answer, the least number of decimal places. So if I took 2.55 plus 1.0 plus a 2.360, and I add all those guys together, give it the old college try here without a calculator. So that's a 0, that's a 1, that's an 8, that's a 9, that's a 2, 4, 5. I think I did it right, hopefully. So we do end up with this number here. Again, we are not looking at significant figures, but we are looking at decimal places. So this first number has 2 decimal places, 1 decimal place, and 3 decimal places. So the smallest number of decimal places is to the first decimal place there, or 1 decimal place. And that means our proper answer in this case should be 5.9 in this case. Why is it the smallest number of significant figures and the smallest decimal places? These are all based on significant figures, basically, and measurements. And that means that your one with the smallest number of sig figs and probably the one with the smallest number of decimal places is going to be your worst measurement out of all that group. And your calculation is only as good as your crappiest measurement, frankly. So the worst measurement is the one that determines how good you could do in terms of your calculation. By the way, the bottom one does have 1 decimal place. How many significant figures does the bottom number have? It has 2 significant figures, right? So you want to keep that in mind because you could be multiplying that number next, right? So you got then switch from like decimal places to now need to look at significant figures and stuff like that. Any questions on that? Now, if you had a combination of something you're doing, like, you take 3.2 times 1.678 divided by 436, and you put all that into your calculator, 3.2. By the way, I would probably not put it all in at once, just so you know. And we divide that by 436. On our calculator here, display, you got something like 1.23155963, basically. So we did multiple steps in this case. And when you are doing sort of multiple steps in a calculation, you do need to kind of keep track of your significant figures throughout the entire calculation, because it could actually be like your first part of your calculation is actually the most important thing that determines where you should end up with your answer rather than the last part. So you should definitely keep track of everything. I personally would probably, good rule of advice is not rounding very hard in terms of significant figures until you get to the end. So you should kind of keep track of everything, clean everything up at the end in terms of significant figures, and not kind of round too much along the way. So basically, math operation tells us that we got some parentheses up there. We should do this part of the calculation first. And we are multiplying, which means that is 2 significant figures. That is 4 significant figures. So for example, if you technically just did the top part of the calculation, you would end up with 5.3696. Now, technically speaking, this number up on top should end up with 2 significant figures, the least amount of significant figures. That would be right here. Yeah. Now, would I round at this point to 5.4? The answer is I would not. Yeah. So I would keep the entire number at this point to do the rest of your calculation. The problem with rounding at every step, especially if you're doing multiple sort of calculations in a row, every time you round, you're going to move yourself further and further away from the correct answer. And it's going to be like rounding error basically along the way. So it just kind of compiles if you kind of do it that way. So some people will just do what I just kind of did there, put a little mark of like, hey, that's like where it should be. Some people will just keep a couple of extra digits, which is good as well. You know, usually if you keep a couple extra digits, 2 or 3 more than you need in a calculation, you know, you will avoid a lot of those sort of rounding errors. Then obviously we are now going to take this number up on top, which is technically supposed to be 2 significant figures. We're then going to divide it here by this guy on the bottom, which is 3 significant figures. And once again, when we're dividing, we are looking at significant figures. So based on our step all the way through, we should have 2 significant figures on top, which tells us we really should have 2 significant figures there. And now at the end, we should end up with only 2 significant figures. And the answer here should be 1.2 in this particular case. So you do want to kind of keep track of it. So that you do end up with the correct number of significant figures. Now, again, if you just rolled with 5.3696 and didn't realize, hey, that's really supposed to be 2 significant figures, you may think that should be like 4 or 5 significant figure, and the bottom one is 3, and you may end up with 3 significant figures and get the wrong answer. So you do have to kind of keep track of your significant figures all the way through. And in this case, it actually is the very first calculation we did that determines where we end up, basically, right? And again, you got to kind of keep that track of it all the way through. Question on that there. By the way, as I mentioned a second ago, I probably would not punch all this stuff into your calculator at once because most people don't do it correctly and most people get a wrong answer. So when you have a fraction like this that you need to basically do, you could take all the numbers up on top that are multiplying. You can multiply as many numbers as you like. You then should hit the equal sign and then divide it by the bottom number. You will always get the right answer in that case. People oftentimes, when they got like a fraction or something like that, they want to punch like everything all at once into their calculator. If you don't use parentheses correctly, your calculator is going to do the wrong math and you will get the wrong answer. So generally speaking, you can multiply as many numbers as you like up on top, hit equals. And then if you have multiple numbers on the bottom, that's usually where people screw up. I would divide by the first number, hit equals, divide by the next number, hit equals, and divide by the next number if there happens to be an hit equals. Don't be afraid to use the equal sign after each time. That usually will tell your calculator, oh, you want to kind of do it this way, rather than some calculators will definitely group it wrong, and people usually get the wrong answer. So just keep that in mind. Any questions on that? Yeah. Was it? What's it? I think it was 400 did I say? Let me see. I don't know. Did I? I did. I did. You might be right. I think I did pipe 4.36. Did I say 4.36? I don't remember what I said. All right. Well, let me do the right numbers here. But actually, let's just put it 4.36. That will do it. Thank you. You are correct. Yes. I guess. Thank you. I think I said 436, and I actually punched in 4.36, which is how I got that number, obviously. All right, so we'll go with 4.36. It doesn't change anything. It still has 3 significant figures on the bottom and 3 significant figures there as well on the bottom. So we would still end up with 2 significant figures, and obviously punch in the right number would even be better on your calculator as well. Yeah. Any questions on that? All right, let's take a look at another one here. Let's say we did 324 times 1.2 divided by, let's go with 6.50. Then we will add 0.3256 to it. All right, see what you get. I'll do as well. Even try to hit the right numbers in there. See how we do. That'd be good. All right, let's take a look. So again, here I would obviously multiply the top first And go with the right numbers here. 324 times 1.2. I'm going to hit equals. And I'm going to divide it by the bottom number there, which is 6.5. That's going to give me, technically on my calculator here, 59.8153846.2. And we're going to do a plus 0.3256. Now, again, here we did multiple things, multiplying and dividing. We did this part first. And again, if we look at the sig figs, that's going to be 3 sig figs. That's going to be 2 sig figs. That means technically our top answers should have 2 significant figures. We divided it then by the bottom number, which is 3 significant figures. So 2 significant figures divided by 3. In the end, we'll end up at 2 significant figures. At this point, really, this answer should be 60, right? Again, rounding up, looking at the 8. Here, we do need to put the decimal point there, right? Otherwise, again, it has only 1 significant figure and not 2. I can't throw a 0 after the decimal point in this case because now it will have 3, right? So that's a problem. And now we're going to add. So we're going to take this number. And again, I'm going to roll with the 59.8 number there and add 0.3256 to it. And if we do that, that is going to get me, looks like 60.14098. And in this particular case, we were technically looking at this number and we're looking at decimal places. And really the top one has no decimal place, right? So we would probably take this actually just to 60 as our whole number in this case. Any questions on that there? So the key here is when you're doing calculations, you want to make sure that that you do keep track of all the kind of sig figs in your calculation. You do, again, like I mentioned, I would avoid really rounding to the end and just kind of clean everything up at the end. If it helps you, you could put a little line over where things should be. But usually, honestly, if you just kind of keep a few extra digits along the way, I personally, when I'm doing things in the calculator, just roll with the whole number that I got and just kind of continue on to the end and then clean it up. So here again, if we look at some more examples, we are multiplying here. So we're looking at sig figs. That is 3 significant figures. That is 2 significant figures. That means our answer should go to 2 significant figures. We do need to round up because of the 7 next to it, and we will end up at 9.4. Here we are dividing, so we're looking at sig figs. That is 4 significant figures. That is 3 significant figures. And again, we're always looking at the smallest for both things, decimal places and sig figs, always the smallest. And that third significant figure would take us to the 8. We would look at the 2 and see it's less than 5 and drop them in this case. And we would end up with this as our answer. Once again, here we cannot add any zeros after the 8. Otherwise, we would have too many significant figures, right? So it wouldn't really change the number meaning, but it would give you the wrong number of significant figures if you add those zeros at the end. Over here, we're adding. So it's decimal points. So 2 decimal points, 1 and 3. Answers should end up at 1 decimal point, and we end up at 29.1. And lastly here, subtracting, same deal, decimal point smallest, 4 and 1 takes us to 1, and we do need to round up because of that 8, and that will take us to 0.6, which again has 1 decimal point and also 1 significant figure in this particular case, if you need to use that in a calculation down the road. Any questions on rounding calculations with sig figs? So when you do calculations, you should always give your answer to the proper number of significant figures. As I might have mentioned when we were talking about scientific notation, sometimes no matter what you do, you got to throw it in scientific notation to get the right number of sig figs. So you will sometimes come across an answer where you just can't leave it in sort of decimal form and have the right number of significant figures. So if you get yourself to that point, again, scientific notation is definitely the way to go because you could kind of control your sig figs by whatever's in front of that times 10 part. Do you have to give all your answers in scientific notation? The answer is no. Again, sometimes it's the only way to do it. And obviously, if the question says give it in scientific notation, you need to. But other than that, you could give it in decimal form. You could give it in scientific notation, as long as your answer has the correct number of sig figs, basically. Any questions? All right. So again, we talked about some of these prefixes, and a reminder that you basically do need to kind of know these. And again, how to use them correctly, as we sort of talked about, I think maybe on that first day. A reminder that when you look at this sort of column here, that is how much there is in the base unit to one of the prefix units. So again, if we look at milli, which is 10 to the minus 3, that means, for example, in 1 milligram, there is 10 to the minus 3 grams. So that is the proper way to use that conversion. Once again, that 10 to the minus 3 is, if you need to punch in your calculator, that is 1 times 10 to the minus 3 in scientific notation. So you would want to make sure you use your exponent button on your calculator, like we talked about with scientific notation, to do that. So for example, if we had 635 milligrams, and we want to know how many grams that was, we could do a conversion and use this equality to do so. And we're going to talk a little bit here. We'll kind of preview what we're going to talk about in a second, but we're going to set it up using dimensional analysis, which is, again, how they do want you to kind of show your work in this class. So from an equality such as this, we can get two conversion factors, and conversion factors basically are just fractions. Say, for example, 1 milligram over 10 to the minus 3 grams, or we could just flip the fraction apart, upside down. 10 to the minus 3 grams is 1 milligram. So these are our conversion factors that you could get from any equality. Well, this specific equality, but from any equality, you could get basically two conversion factors, and they're basically just fractions. One thing goes on top, the other goes on the bottom, then you just flip it and put the other guy on top and the other guy on the bottom. And we use this with how we show, for example, our work in chemistry, and it is basically what is known as dimensional analysis. And the idea of this is we use conversion factors and we set it up so that we could see the units canceling out. And basically, the good news is it's a very simple concept, and it's basically this concept of opposites cancel. So if there is a unit that you want to get rid of, and it's on the top, you need to put the same unit on the bottom. Opposite location cancels. If the unit you want to get rid of is on the bottom, you got to put the same unit up on top, and it cancels each other out. Why does that work with units? So for example, if you had like grams on top and grams on the bottom, they cancel each other out basically because they're the same unit. It is no different than if you took a number, like 2 divided by 2, basically cancels each other out to 1, right? You take 4 divided by 4, it equals 1. If you take grams on top, grams on the bottom, and divide them, they cancel each other out, basically. So the idea of sort of dimensional analysis and how we sort of set these sort of problems up is we basically just kind of think of everything as fractions. And the basic easy way to do it is just to think top and bottom, basically, and where you want to get rid of those units. So if I were to do this problem, I would start with what was given to me, which was 635 milligrams. Now, although this is not written as a fraction, it basically is over 1, right? So if you wanted to help yourself out, if you're not sure, and you don't need to do this, but you can just to kind of see, you could put it over 1 and make it a fraction, right? What that does show us, hopefully, is when I look at the units of milligrams, they are on top. And I don't want milligrams anymore. I want grams, right? So I want to get rid of milligrams. So when I go look over here to my right where my conversion factors are, I have an option of this conversion factor and this conversion factor. And the one where milligrams is in the opposite location is the bottom one, right? And it makes it very easy to determine what conversion factor I should use. It has the unit in the opposite location. So I'm going to set this up. And again, this is basically dimensional analysis. We're going to set up, I like to use parentheses in a line. Some people like to use straight lines or railroad ties, whatever they call it. I don't know. But we're going to go 1 milligram on the bottom, 10 to the minus 3 grams up on top. And this is basically the setup for dimensional analysis. And this is basically how you are supposed to show your work in chemistry. Yeah. So it's basically this kind of concept here. Now, what do we do in terms of math? And what are we doing in terms of math? The nice thing when you set it up with dimensional analysis like this, you're only doing 2 math steps ever. Anything that's on top gets multiplied. So however many numbers you got on top, you are multiplying. And whatever's on the bottom gets divided. So it's a very simple, like, I'm not sure what I should do math-wise. Anything on top, multiply. Anything on the bottom gets divided. And because what we're dividing on the bottom, basically the milligrams and the milligrams will cancel out because they're getting divided out. Milligrams divided by milligrams, basically. And the only unit left at this point is grams. So basically here, all I have to do is take my 635 and times it by 1 times 10 to the minus 3. And again, you want to make sure you use your exponent button. And you will end up with 0.635 grams in this case. First off, any questions on that setup? So this is dimensional analysis. This is basically how you show your work. The other good thing about dimensional analysis is when you set it up like this, the only thing you are doing is multiplying and dividing, which means when I come to my answer, the only thing I should be concerned with is significant figures because it's all about multiplying and dividing, right? So it's all about sig figs. I don't have to worry about decimal places or anything like this. And in most cases, it's just about significant figures. So let's talk about significant figures. Where should my answer end up? Now, when we look at this conversion factor that we use, this guy right here is a metric to metric conversion, which means that this is a exact number, which means I don't have to worry about that in terms of my calculation. That means the only number that I have was my original number, right? And my original number had how many significant figures? 3. That means my answer here should have 3 significant figures. So the nice thing about dimensional analysis is if you write it like this, which you should if you want full credit, yeah, in all chemistry classes, you need to write it like this. And the nice thing is you always know what you're doing mathematically. You're multiplying the top, dividing the bottom. As we'll talk a little bit more about maybe later on, a benefit of dimensional analysis is if you know how to do it correctly, you may not even have to worry about a formula because all you have to do is go, okay, I don't need these units and I got to get rid of these units and keep these units. And you could a lot of times just use dimensional analysis and it will kind of rearrange formulas for you, do the math for you just by getting rid of the units you don't want and keeping the units you do want. And you don't even have to remember like, hey, D is equal to M over V or anything like that. You know, you could just kind of do a more dimensional analysis approach. And a lot of times you don't even need a formula because it'll kind of just self-do it as you're doing the calculation. Any questions on that there? All right, so again, with these prefixes, you definitely want to also, a common error sometimes people make is if they are kind of doing a conversion, for example, from one prefix to the next, and they just want to kind of like move decimal places, and most people screw that up and stuff like that. So besides the fact that you do need to show your work, you can't just like move decimals and stuff like that if you had to do a conversion like that. I would always recommend taking the prefix unit back to the base unit and from the base unit to the next prefix unit. So for example, if we were doing like, let's erase all my scribble on this page here. So let's just say we were doing 5.2 kilometers to millimeters, right? Now, sometimes people will want to kind of just directly go from kilometers to millimeters. And like I said, very often they will screw it up and not sure how to kind of do the conversion. So what you can easily find on this chart, obviously, is the kilo conversion, which will take you back to meters. And you could also find easily, obviously, as we just did, the millimeter conversion, which will then take you back to millimeters. And that is the way I would highly recommend you show your work and set it up. And you won't probably screw up moving decimals in the wrong location or doing the wrong kind of conversion between them. So if we were going to do that, why don't you do that? Actually, why don't you try it? Go ahead, set it up, sort of dimensional analysis, use conversion factor. And how much is 5.2 kilometers in millimeters? So set it up using it and see what you come up with. We'd obviously want to maybe find our pathway there. And like I said, it's always a pretty good idea to take it back to the base unit before you go to that or prefix unit. Again, you do have to show your work pretty much in chemistry, so just moving decimals is not going to really do it for you in terms of a problem. So obviously kilo, we got a prefix, and we got milli, which again is 10 to the 3 for kilo, 10 to the minus 3 for milli. And that, once again, is 1 times 10 to the 3 for the kilo and 1 times 10 to the minus 3 for the milli. So as we just saw a second ago, that basically means in 1 millimeter, there is 10 to the minus 3 meters. That will get us basically 1 millimeter over 10 to the minus 3 meters, or 10 to the minus 3 meters over 1 millimeter. And these again are our conversion factors. That's our equality. And obviously for kilo, we could do the same thing. That would mean for our equality for kilo, in 1 kilometer, there is 10 to the 3 meters, giving us, again, 2 possible conversion factors. 1 kilometer over 10 to the 3 meters, or 10 to the 3 meters over 1 kilometer. First off, any questions on where I got all that from there? All right, so we're just going to start our calculation here. We're going to start with 5.2 kilometers. Again, you do not have to do this, but if it helps you just kind of visually see kind of where the units are, you could just put it over 1. Once again, you don't have to do that if you just understand that that's on top, those units and stuff like that. So again, we're going to go from kilometers first off to meters. We want to choose the conversion factor that's going to do that. So since our kilometers are on top, we need it in the opposite location to cancel. So we'll take the one on the right there, and that's going to get me 1 kilometer is 10 to the 3 meters. If I were to basically stop my calculation right at this point, the kilometers on top and the kilometers on the bottom would cancel, and I would be in units of meters, which again, because I am setting this up correctly, I can also clearly see meters are still up on top, right? So are on top, and I want to get rid of meters now and end up at millimeters, right? So because meters are still up on top, once again, to cancel those meters, we're going to go opposites. So that helps me choose the right conversion factor over here, where meters are on the opposite location. And I'm just going to continue my calculation. And I'm going to go with 10 to the minus 3 meters on the bottom and 1 millimeter up on top. The meters on top and the meters on the bottom will cancel. Now, you absolutely could have, if you wanted to, just get an answer after the first calculation and then use that and do the second individually. Or it's sometimes just easier just to kind of continue your calculation through there. Once again, math-wise, what we are doing here is we are multiplying anything that is on the top. Then I would hit the equal sign, yeah? Then we're going to divide anything that is on the bottom, basically. And again, between the two, I would hit equals, although there's a 1 on the bottom, so it doesn't really matter that much. But if you had a real number there, I would hit equals in between. So if we do all that good stuff there on the handy dandy calculator, remember we do want to use our exponent button as that's 1 times 10 to the 3. And we're going to divide what's on the bottom, which again is basically 1 times 10 to the minus 3. And that is going to get us an answer of 5.2 times 10 to the 6 millimeters. Yes. First off, any questions on that calculation there? Now, when we look at significant figures in this case, that is an exact number, right? That's a metric to metric deal. So that's exact. So we don't have to worry about it. That is also an exact number because it's metric to metric. That means, like I would say, probably 98% of the time, if you're just doing a dimensional analysis, usually that first number oftentimes has kind of the right sig figs. Not always, but in a lot of cases it does. So 2 significant figures, which means I am okay here with 2 significant figures, right? Because I'm in scientific notation, right? If I did all my zeros without scientific notation, I do need all the zeros, but I should not put a decimal point at the end of it either, right? Otherwise, you would have way too many. Any questions on that? Millimeters is a smaller measurement, right, than kilometers, which is a larger measurement. So it does sort of make sense. You would have a lot more of the smaller guys than you do the larger number. You know? Any questions on that there? So again, in terms of this class, and we'll kind of jump ahead here a little bit, this is what you need to show in terms of your work. Yeah, so you do need to show it's set up like that with dimensional analysis, with the proper conversion factors, the units all the way through the calculation, and your answer to the right sig figs. Any questions on that there? All right, so obviously, as we talked about a little bit earlier, again, I would say that probably everything on this screen are some conversions that you should definitely know. We do come across these length equalities a lot, so make sure that you do, again, know these guys. We saw some of these at the beginning, I think. Volume, I would definitely say probably out of all 3 of those, that's definitely the one, again, that you're going to see the most here in chemistry. 1 liter is 1,000 milliliters. This, again, is sort of the whole number equivalent to 10 to the 3, right, or 10 to the minus 3 in terms of milli. We also talked about this last time. A cubic centimeter is equal to 1 milliliter. And a lot of times, if you're doing something with medicine, it is sometimes referred to as a cc. Or watch a medical show and they say, give that guy 5 cc's of that. That's 5 milliliters, basically, right? So that's basically what they're giving them. Again, we do get this volume measurement, as you can see there, by really taking 3 length measurements of like the length times the width times the height, as we talked about the other day. If you did all those sort of length measurements for like a cube, and you did them all again in centimeters, that is how you get to your cubic centimeters, which once again is a volume, not a length, while all these individual guys are length measurements. So basically, if you take any length measurement, typically and you cube it, it is talking about a volume. In terms of qualities for mass, again, these are some pretty good sort of ones to know for sure. In addition, obviously, that 1 pound is 453.6 grams. That obviously is an exact conversion. That's obviously going from metric to English sort of conversion as well. Yeah. All right. Let's get through those. So we sort of touched upon this a second ago, but just to officially talk about conversion factors, basically from any equality that you have, you again can write 2 conversion factors, which, as we saw there in those examples, are really just fractions. And an equality, again, is anything that basically represents the same amount but are on different scales. So our 100 pennies, right, is equal to $1. They both represent the same amount of money, but they are on different scales. And this again is an equality. And from that equality, as I mentioned, you can write two usable conversion factors. And will you use both conversion factors in a calculation? The answer is no, because you'll be undoing your calculation, basically, right? So again, you just want to use whichever one is appropriate. And you do want to get in the habit of sort of doing these calculations and writing these things as very clear fractions, yeah, where the units are on top and bottom. And it just makes everything a lot easier in terms of the calculations you do. And it hopefully will help you not screw up where a lot of people do, where a lot of people will kind of just stack the units, like, grams times, whoops, milliliters divided by, grams times centimeters. I'm not sure if they should be dividing, multiplying. And you do want to make sure that you really keep the units sort of separated as well. So if you have something that has 2 units, like, 4.2 grams per milliliter, you could use that as a conversion factor. The number usually stays with the top unit, and the bottom unit is usually 1. And you could do something like 4.2 grams over 1 milliliter, or 1 milliliter, 4.2 grams. And again, by breaking those units up, top and bottom, when you get to the calculation part, it should make it a lot easier in terms of should you be multiplying, should you be dividing, what conversion factor to do, rather than keeping those 2 units together all up on top, and you're not sure if you should be multiplying, dividing, and stuff like that. So you want to kind of separate those units, keep everything in a very clean sort of fraction setup, and that just allows you just to remember basically 3 things. Opposites cancel, multiply the top, divide the bottom. Yeah, and that's all you have to remember, basically. All right, so that's our penny example, obviously. Here's a table of some common equalities. I'm just going to say probably most of the stuff on here, you should probably know, to be honest with you. So it probably also will encompass a lot of those earlier ones as well that maybe we saw on some of those earlier slides. Definitely the feet in inches we see a lot. Maybe somebody mentioned it earlier. The feet in miles conversion is used a lot, 5,280 feet in a mile. Gallon and quarts does seem to pop up. And definitely I would say everything in that metric sort of column, for the most part, you will come across a lot. So maybe just a deciliter one you might not see all that much, but most of everything else you'll see there. And then in the last column, we have metric to US sort of crossovers. And remember that some of these are exact numbers. So this is an exact number. My bad teaching, sorry here. Okay. They do want you to use 453.6 grams is equal to 1 pound. And remember, that was also an exact number, so we'll use that one here. So let's talk about when we use these. Obviously, all these are equalities, and from any of these, you could write 2 conversion factors to use in a calculation. Let's talk about sig figs and when we should worry about sig figs. So if you're pulling anything from this column, you're good. That's pretty much all exact, right? So it's US to US sort of conversions. You don't have to worry about, sig figs in a calculation. If you're pulling anybody from sort of this column, or obviously anything that is a metric to metric, as we talked about before, also you do not have to worry about it, as it's going to be an exact number. If you pull from this very last column, you do have to look at it, except for obviously the ones that are listed there that are exact. Other than those, you do have to look at it. So for example, if you were doing a calculation that involved this equality here, 946 milliliters is equal to 1 quart. That again is a metric to English sort of conversion. You do have to look at the significant figures if you use that as a conversion factor. What number would you look at in terms of significant figures? You would look at the actual one that's not a 1, so the 946. So this would count as 3 significant figures if you were using that in your calculation. You would not look at the 1. So in most cases, if you're kind of doing a metric to English sort of conversion, a lot of times one of the numbers will be 1. So you would look at the other number as in terms of how many significant figures you are. So if you cross over English to metric, you do have to take into consideration when you're setting up your calculation and doing your calculation, say with dimensional analysis, you do have to look at the significant figures in those conversion factors. If they are not an exact one, like the 1 inch is equal to 2.54 centimeters. I will say still, a lot of times, even if you do have to look at one of those, still that first number oftentimes is super close or the right number anyways. But sometimes it is the conversion factor you have to look at. So when you're using conversion factors that cross over, you do have to look at the significant figures. The other place where you do have to look at significant figures for conversion factors is a conversion that is given to you in the problem. It's not like a true conversion, like 12 inches is a foot always, right? You know, you may be in a problem, for example, driving 60 miles per hour, right? You don't always drive 60 miles per hour, right? But specifically in that problem, you could use that as a conversion factor, and you would have to look at the significant figures in that. So if you're given some piece of information within the problem that is sort of specific to the problem, you typically do have to kind of look at the significant figures for that number when you're doing the calculation as well. So those are really the two places where you're using conversion factors that you do have to kind of worry about the sig figs. English to metric crossover or any type of conversion that's sort of just given to you in the problem. Other than that, you could almost just like blow right by them and go, I don't have to worry about them in most cases. But those are two places where you do. Any questions on that there? All right, so obviously here, if we have 5,280 feet in a mile, we could write our two conversion factors as we've been talking about. Again, they're basically just fractions, so one on top, one on the bottom, as to which one that you want to use. Again, we may be given something like I said a second ago. Maybe you are driving 65 miles per hour. So if you're given something in words that says something per something, that's a fraction. Yeah, so 2 units, one on top, one on the bottom. And basically what 65 miles per hour means is if you roll 65 miles per hour continuously, in an hour, you could go 65 miles. That's basically what that means. Good luck around here. You'll never be able to do that, but you never have a wide open stretch of highway. Ideally, you hit 65 miles in 1 hour is basically what that means. Or if you go for an hour, you should have gone 65 miles. Once again, same idea here. The 65 stays usually with the first unit, and the 1 is with the second unit. If you go fill up at the gas station, some 91 octane for $3.05, which, believe it or not, was super expensive when I made this slide years ago. Now you can't even find 87, I don't think, for $3. But basically what that means, right, is for every gallon of gas you pump, you got to pay $3.05, right? Or if you have $3.05, you can get yourself 1 gallon of gas, which might get you down the road a little bit. Now, another very common thing that we sometimes do find in problems, and we sometimes need to kind of convert into conversion factors, are percentages. And if you have a percentage of something given to you, the easiest way to convert a percentage into like a usable conversion factor is to simply just assume you have 100 of something, right? And it basically keeps the number the same. If you got 72% on your exam, that probably meant you got 72 points out of 100, right? So it just kind of turns it into a very easy way of doing that. So if we had something that was 12% body fat by mass, you could do 12 kilograms of body fat for 100 kilograms of body mass, or 100 kilograms of body mass gives you 12 kilograms of body fat. You could also do more of an English conversion. 12 pounds of body fat is 100 pounds of body mass, and that would get you obviously 12 pounds. This is getting cut off there of fat divided by 100 pounds of mass, or 100 pounds of mass 12 pounds of fat, basically. And that is super the easiest way. And we definitely come across a lot of things in chemistry that are given to you in percentages. And again, it is a lot of times easier to set things up with dimensional analysis. So just turning those percentages into conversion factors, setting things up with dimensional analysis, like I said, will actually allow you to sort of bypass a lot of formulas that you don't have to worry about and remember, stuff like that. All right, so obviously we've been talking about it, but dimensional analysis, and sometimes people just simply call it problem solving, again, is the way that you do need to show all your work in here, as we've been talking about. And once again, that is basically just a conversion factor where we get rid of the units we don't want, and we end up with the units we do want. And once again, we are always multiplying the top and always dividing the bottom here. And that's always the way that we do it. By the way, if we do have two units that we want to get rid of, right? We want to keep them separated from each other and just approach it the same way. You know, if we had unit A over unit B, I may want to just get rid of unit A first, so I could just go like unit A and unit C. That's going to cancel. Now I can see my unit B is on the bottom, so I want to put unit B up on top to get rid of it. And my imaginary conversion here, my unit B, and try to remember the alphabet here, units D will go with. Those guys will also cancel. Now I'm left with, for my answer, by the way, unit C divided by unit D, right? So if you have two units that are on top and bottom and they are not the same, they do not cancel and they stay at the end with the answer. Yeah, so same deal. Typically when you get to the answer, if you had two units, top unit gets the number, bottom one is just one, basically. You don't put the one, just leave it the bottom unit by itself. But we do divide. Also, a really important thing with dimensional analysis is get an answer. Yes, not a fraction. So do not give an answer as like, 432 miles over 620 hours. Yes, divide it and get an actual number with the proper units that are left over. So here are the steps to a dimensional analysis problem. And for the most part, if you follow these steps along the way, it should get you the right answer. It's a really good idea sometimes to write what is given to you. And you want to probably maybe figure out what you're trying to find. Then you want to find the appropriate pathway to get you to your answer. And again, if you're doing a straight conversion, it could be multiple ways you go, depending on what conversion factors you use. So there can be multiple ways to get to the same answer if you choose sort of legitimate conversion factors. But you want to think about what equalities will get you there. You want to think about what conversion factors you have for that. And the most important part for credit, number 5, you need to set it up like we've been doing there with the fraction, the units, and you should also solve the answer. It would be great as well. And get an answer with the proper units and proper sig figs. All right. So obviously here, if we want to know how many pennies are in $3, once again, this is a pretty straightforward one. We want to go obviously from pennies to dollars. And that gives us our 100 pennies is equal to $1. That gives us our equality. And our conversion factor is obviously 100 pennies over $1. Our $1 over 100 pennies. So starting with what was given to us, our $3. Again, if you want to write the 1 underneath it, you can, but you don't need to. Just remember it is up on top. And obviously opposite is going to cancel, so we're going to go there. We'll go $1 on the bottom and 100 pennies up on top. We're going to multiply and then divide. That is going to cancel. That's going to give me 300 pennies in this case. In terms of significant figures, I do not need to worry about that, right? Because that's an exact conversion. That means over here, this basically is one significant figure, which means my answer should have one significant figure. So here I would not want to put a decimal point after the zeros, right? Because then I would have three significant figures. Nor would I want to just leave it at 3, because although it does have one significant figure, 3 pennies is a very different amount, right, than 300. So you would be changing the meaning of the number. Any questions on that there? All right, let's try one here. All right, you go to local AM PM, you get yourself 32 fluid ounces of drink, Diet Coke from the Thirst Oasis. Of course, everybody goes crushed ice, right? Nobody goes cubed, right? Crushed ice is the way to go. How many gallons of Diet Coke did you drink? Here are some equalities that might be helpful. And obviously our conversion factors we could get from those equalities. So why don't you take a moment there and see what you end up with. Okay, let's take a look. So like I said before, here we basically want to go from fluid ounces to gallons. And one pathway is we could go from fluid ounces to quarts and then take the quarts to gallons as sort of our pathway to get there. Again, we can find the equalities that will allow us to do that. And obviously from each of these equalities, we could have our two sort of conversion factors to choose from. Once again, we're obviously not going to use them all. We're just going to use the ones that we need. So we're going to start with our 32 fluid ounces here. And once again, if you want to put a 1 underneath it just to help you visualize it's on top, you can, or you do not need to. But it is on top to start with. And that means that we do want to get rid of fluid ounces. So we want the opposite location. So once again, that's going to make our choice of conversion factor pretty easy. The fluid ounces is on the bottom in the opposite location. So that is what we're going to do. We're going to do a 1 quart is 32 fluid ounces. Once again, we are multiplying the top. We are dividing the bottom. And because we're dividing, that is going to get rid of fluid ounces at this point. If I were to stop the calculation right at this point, I would be in units of quarts, which are up on top, as we can see. We don't want to stop there at quarts. We want to go to the next one, which is now take it to gallons. Again, using our quarts and gallons conversion and our two possible conversion factors. By setting it up like this, I could clearly see quarts are up on top. Once again, opposites cancel, so that is where quarts are in the opposite location, and we're going to do that as well. 4 quarts on the bottom, 1 gallon up on top. And once again, we're going to continue to multiply the top and divide the bottom. By dividing, that is going to get rid of our quarts. That is going to leave us gallons up on top. And typically speaking, if you are solving for a 1 unit answer, that unit should always end up on top. If it ends up on the bottom, you solve for the reciprocal of the answer you're looking for. If you have 2 units, those 2 units need to end up in the proper locations, top and bottom, as to where they should be. So here we got gallons. So basically in this case, we got a 32 divided by, basically 32 divided by 4. And the answer here again is 0.25 gallons. As I mentioned a second ago, divide it out. Don't leave an answer in a fraction. Makes me think you're just too lazy to divide it out. Yeah. As an example, I have had people write things like 562 miles over 320 hours and box it. So never leave an answer in chemistry as a fraction. Always divide it out, get a decimal type number, and take it to the proper number of sig figs. Let's talk about the proper number of sig figs. Well, I think we're good on these guys in terms of exact numbers. That means if we come back to our original number here, it has 2 significant figures. And that's good because that has 2 significant figures as well. And that is where we should end up in this particular case. Any questions on that? Do you need, again, show all of this for credit? Again, the answer is no, but if it helps you to do so, you can. You don't need to show the equalities. You don't need to show the conversion factors. You don't need to show given or find. once again, you need to show the calculation with the dimensional analysis setup and the answer with the proper number of significant. Like I said before, there are multiple ways that you could get to the same answer. So as long as you use a legitimate conversion factor, that is legitimate, you could do it as well, as long as you show the work to do that. And like I said, there are multiple ways, depending on what conversion factors you may choose or equalities you may choose. There may be a different pathway to get you to the same answer as well. Other questions? We're going to continue on. So we're off to another example here. An antibiotic doses is 500 milligrams. If it is supplied in 250 milligrams in 5 milliliters, we want to know how many milliliters would be given. So a couple of conversions that might be helpful for it. See what you come up with there. Okay, let's take a look and see. So in this case, we want to give 500 milligrams. And in this case, it is given as 250 milligrams per 5 milliliters. So this is a conversion factor that, once again, is sort of given to us in the problem. And because of that, we can really use it as a conversion factor. So we could use it the way it's written there that I just circled. We could also flip this around if we needed to, 5 milliliters over 250 milligrams. So again, we could use that either way. We're going to start with, we want to give 500 milligrams. Once again, that is going to be up on top. So again, dimensional analysis to cancel. Opposite locations for the same units. We're going to want to use it in this fashion here on the right. That's going to put our 5 milliliters up on top, our 250 milligrams on the bottom. Once again, we are going to multiply and divide here. Milligrams are going to cancel. And that's going to end up with 10 milliliters in this particular case. First off, any question on the setup here? We now want to think about significant figures, right, and what our answers should be. So we definitely want to look at our first number here. And the way the first number is written is that is 3 significant figures. We do have to actually look at this conversion factor. Once again, that is sort of specific for the problem. That's not a every time sort of conversion. So in this case, we actually do have 2 numbers written, and we do have to look at both of those numbers because they're not both 1 or anything like that. So this would technically have 2 significant figures. That guy would actually have 2 significant figures. That means that our answer here should end up with 2 significant figures, which my answer right now has only 1 significant figure, as I have no decimal point there. So I do need to put a decimal point there. And now I will have 2 significant figures. Could also do scientific notation, 1.0 times 10 to the 1 if you wanted to. We cannot, though, right, put a 0 after the decimal point, right, because then it will have 3 significant figures. So we don't want to do that. Yeah. Any questions on that there? So 2 sig figs there for our answer. All right, let's take a look at another one then. A patient receives 5 pints of plasma. How many milliliters were they given? Let's see what you come up with. Set it up, dimensional analysis, conversion factors. So in this case, we're really starting with pints, and we want to get to milliliters. So again, you could find a pathway that will get you there by looking at some equalities. Obviously here, from what I chose, I could go from pints to quarts, and then quarts over to basically milliliters in a sort of 2-step fashion. I would say in most cases, 2 to 3 steps is probably all you will need to kind of get yourself converted to the right units. So obviously those equalities will give us those choices of conversion factors that come next. We're going to start with our 5 pints. Once again here, our pints are up on top. So just keep it simple to cancel opposite. So that is the opposite location for the pints. We're going to go 2 pints. There is 1 quart. Again, we're multiplying and dividing here. Pints are going to cancel. Once again, if I stop my calculation right at this point, I'm in units of quarts. They are clearly on top, which is going to help me finish out the rest of the calculation. Again, you could get an answer at this point, but since you need to continue on, might as well just continue on. Quarts are on top. I want to get rid of them. So when I go to my next set of conversion factors, I need quarts in the opposite location, which is this one here. That's going to put my quarts in the opposite location and my 946 milliliters. Once again, still multiplying on top and dividing on the bottom there. The quarts are going to cancel. So basically in this case, we're going to take 5 times 946, going to hit equals, going to divide it by 2 on the bottom. That's going to get me 2365. The units left are milliliters at this point on my calculator. Again, we need to look at some significant figures. Our very first number here has 2. This we don't need to worry about as an exact conversion. How about this one? Do we need to worry about this one? We do. This is a crossover conversion between English and metric. We would look at this number, which has 3, but still, that is the lowest since we're always multiplying and dividing. So we do want to go to 2 significant figures, which would take us to the 3. We would look right next door at the 6, and that 6 would tell us that we do round up, and we will end up with 2,400 milliliters. Or obviously, again, you could do a little scientific notation if you like. To the 3 milliliters. Once again, here we do not want it to add zeros in our scientific notation, nor do we want to put a decimal at the end of it. Otherwise, it will have too many significant figures in terms of our answer. Any questions on that one there? All right, and once again, this is what you need to show for credit on the bottom there. All right, let's take a look at one more here. You are stranded 125 miles away from home. You got no money. You decide, it looks like a nice day outside. Let's take a nice walk. If you walk on an average of 55 feet per minute, how many days until you find yourself home if you don't stop, I suppose? All right, here are some equalities and some conversions that might be helpful for you. Set it up dimensional analysis. See how many days you're walking for. Yeah. All right, so let's take a look and see. In this case, we want to go basically 125 miles, and we're walking at a rate basically. And once again, sort of a conversion factor. This rate is given to us in the actual problem, and we can use it as a conversion factor as 55 feet per minute. Or once again, we can flip it around, and we could put the minutes up on top, which would be 1 minute and 55 feet. The rate is basically, right, a distance per time. We have a distance and we want to end up really with a time. So that rate is really the conversion factors. It's going to take us from distance to basically time, right? We do have a little issue though before we can use the conversion factor, and that issue is the length measurement in each of them or the distance, whichever one you want to call it. They are different. One is miles, one is feet. They are not going to work together correctly if you don't do a conversion. So you could either convert the miles to feet and just use the conversion factor the way it is, or you could convert the feet in the conversion factor of feet per minute into miles per minute and use it that way as well. I'm going to choose to take the miles, 125 miles, and first convert it into feet. And then I'm good to go with my kind of conversion factor that was given to us. So we could see our equality here that we could use to go from miles to feet. And I'll take my 125 miles. I am going to go opposites here. So I do want the 1 mile on the bottom and up on top, the 5,280 feet as my conversion. Once again, multiplying the top, dividing the bottom, miles cancel. That ends up giving us 660,000 feet. Definitely got your steps in. 660,000, I think. Got all the zeros there. And that is feet. Now that I do have it in feet, I am good to go with, again, the conversion factor that was given to us in feet. Obviously, like I said, you could take the conversion factor into miles. So I'm going to start with that, 660,000 feet. Once again, that's going to be up on top. So I do want feet on the bottom. So I do actually want to use the conversion factor in the sort of upside down version there. And we're going to put for 55 feet per minute here. If I stop right at this point, my feet are going to cancel, and I am left with minutes up on top. I now need to go from minutes basically to seconds, or days, I'm sorry. So there are a couple ways you could do that. Obviously, there is in 1 minute. I'm sorry. Let me do that right. I have another question in my head right now. We're not going to seconds, we're going to days. There are 60 minutes there in an hour. That was better, I think. That is going to get us the minutes canceling out as we divide. We now could go from hours to days. And again, opposite cancel. So we want our 24 hours on the bottom and our 1 day up on top so that those cancel. Once again, everything up on top gets multiplied. Everything on the bottom gets divided. So basically 660,000. There's really nothing to multiply up on top. Everybody's a 1 basically. Again, even if the number's not written there, it's assumed to be a 1. And we're going to divide by the bottom. So again, I would perhaps not put all those numbers in at once. I would take the 660,000, divide it by 55, hit the equals button, divide it by 60, hit the equals button, and divide it by 24 and hit the equals button. And you will always get the right answer if you kind of break it up that way. Again, if you put them all in at once, might not be right. 8.333, a bunch of threes, days. All right. Now we need to kind of figure out sig figs where we should go. Obviously here, this is an exact number, so we don't have to worry about it. That's an exact, we don't have to worry about it. That 55 feet per minute is a conversion factor that was given to us in the problem. We do need to look at it. I'll be with you in just a second. 3 significant figures here. And we do need to look at this number, but we do want to be careful when we look at this number because this number does not really have the right sig figs because it was based off of this number, right? And that number really is 3 significant figures, which means that this guy actually should be 3 significant figures, even though I did not write it as 3 significant figures here. So basically we're comparing 3 significant figures with 3 significant figures. That means in this case, we should end up with about 3 significant figures, 8.33 days, it looks like in this particular case. Yes, sir. Have a conversion factor that is part of the problem, so we cannot just ignore it. We do have to kind of look at the sig figs. In this case, it actually ended up being the correct amount. We do want to also be careful in a situation like this as well, that in case you do kind of carry over a number on a conversion, you do have to kind of go back to where that one started and figure it out in that case. All right, question on that there. All right, let's take a look at maybe just a couple more here just to make sure before we move on from conversions. Let me just erase all this stuff here. All right, why don't you try these two and see what you end up with. Why don't we do, let's say you were driving 78 miles per hour. What would be your speed in feet per second? And let's say you had 4.2 cubic feet. What would be that in, I'll do cubic centimeters. All right, so a few conversions that might be helpful. Some we've seen already. 5,280 feet is a mile. 12 inches is a foot, and 1 inch, 2.54 centimeters. All right, take a few moments there. Again, set up dimensional analysis and see what you end up with in each of those. So on the first one here, we actually have 78 miles per hour, and we actually have 2 units that we need to convert. We basically need to convert the miles to the feet and hours to second. And again, it's really important here, as I mentioned earlier, to make sure that you do set up things with dimensional analysis so you can understand where each of those units are. And again, you could really just take the same approach. You could just think of it as 2 conversions that you're going to do in one problem. You could either start with the top or the bottom one. It doesn't really matter. So here, what we would want to do, obviously, is start with our 78 miles per hour. And again, you definitely want to kind of write it like that so you could clearly see top and bottom. It is notoriously bad for people when they don't do that on these type of problems, because they end up dividing when they should be multiplying, or multiplying when they'd be dividing and stuff like that. So it's a very common error that happens. I'm going to start with the miles and just take care of the top part of it, which is it needs to end up in feet. And obviously to do that, I could use this equality here, and we're going to go opposite. So miles are on top. I want a mile on the bottom, and I want my 5,280 feet up on top. We are still doing the exact same thing we've been doing, multiplying the top, dividing the bottom, and that's going to get rid of the miles at this point. And if I stop my calculation right at this point, I am in units of feet on top per hour, right? So feet on top, hours on the bottom. I am good in terms of the top unit because I just need to get it to feet. Now for my bottom unit, I need to get the hours to seconds. Clearly there's multiple ways you could do that. You could go hours to minutes, minutes to seconds. You could also just go seconds to hours if you understand there's 3,600 seconds in an hour, whichever way you want to kind of do that. So we'll just go the longer way here just to use sort of common ones. Again, hours are actually on the bottom. So in this case, 1 hour should go up on top. 60 minutes should go on the bottom. Hours on top and bottom will cancel. If I lay up my calculation right at this point, I'm in feet per minute on the bottom. Minutes are still on the bottom now. I need to get rid of minutes. So to go opposite of that, in a minute, there's hopefully 60 seconds. Yeah. And again, minutes on top and minutes on the bottom are going to cancel. Now the only 2 units left are feet up on top, seconds on the bottom, which is exactly, again, what we're looking for in this case. We're going to multiply everything on top, come back and divide by everything on the bottom. And if you do that, 78 times 5,280 divided by 60 hit equals, divided by 60 hit equals. That will get you a 114.4. Once again, we do have 2 units here. So the number stays with the top unit, and it is basically one of the bottom unit in this particular case. Again, I can't tell you how many times people will do this problem. They'll end up multiplying the 60s instead of dividing. So if you keep it nice and clear, top and bottom, it should definitely help you avoid that sort of really common error. We do still have to look at sig figs along here, right? So let's take a look at where we should look at some sig figs. Really don't have to worry about this guy. Don't have to worry about this guy. Don't have to worry about this guy. So that means really it is this one right here. And that is 3 sig figs. That means my answer here should actually end up with 3 significant figures. That's going to take me to the first 4. And because that is 4, we're just going to drop it, and basically 114 feet per second in this case. Yeah. Any questions on that calculation there? So, like I said, if you have multiple units, definitely make sure the fraction is pretty clearly top and bottom. And it will oftentimes, like I said, it'll kind of avoid a lot of very common errors that people make. All right, taking a look at the next one, we're looking for cubic feet to cubic centimeters. We basically could take kind of feet to inches inches to centimeters to kind of get us there. So here we're going to start with 4.2 cubic feet. Oops. And I'm going to use my feet to inches conversion here. I'm going to do 1 foot on the bottom, which is opposite, and 12 inches up on top. By the way, will that completely cancel out the cubic feet? The answer is no, because that's cubic feet. You basically just took out one of them. You still got 2 to go. So technically speaking, you don't have to do this conversion once. You need to do it not twice, but technically you do need to do it 3 times, as 1 foot, 1 foot, 1 foot is a cubic foot that will cancel out the cubic feet that we have on top. By the way, what we're left with up on top is, at this point, cubic inches, right? Which means we can now use our inch to centimeter conversion. We also technically have to do it 3 times. And again, we're going to go inches on the bottom. 1 inch is 2.54 centimeters. And again, we need to do it not once, not twice, but actually 3 times. Good thing it wasn't 4. There we go, 2.54 centimeters. 1 inch, 2 inches, 3 inches is inches cubed to take care of all those guys. That now leaves us centimeters cubed as our final unit. And again, we're going to multiply the top there. So 4.2 times 12 times 12 times 12 times 2.54 times 2.54 and a times 2.54. There's really nothing on the bottom to divide. Everybody's a 1, so you don't really have anything on the bottom there to divide. That's going to give us a big old number, 118,930.7557 on our calculator. These are going to be cubic centimeters. We now want to figure out what we need in terms of sig figs. Obviously, all 3 of these is an exact conversion. That's one of those kind of few metric to English that's exact, so we don't have to worry about it as it's exact. We don't have to worry about our inches to feet as it's exact. So it is going to be 2 sig figs here. And in this particular case, you may want to go scientific notation, so you don't have to write so many zeros. So we should end up with 1.2 times 10 to the 5th cubic centimeters in this particular case. Yeah. First off, any questions on that? Now, could you set it up like this, where you just go 4.2 cubic feet and go 1 foot is 12 inches in cubit, and then do 1 inch is 2.54 centimeters in cubit? The answer is you absolutely can. The other answer is I probably wouldn't do that, because I can't tell you how many people's papers I see when they do something like that, they never live to actually do the number 3 times. They like do the units and never do the actual numbers. It's like a super common error. So sometimes if you see the numbers in front of you, you know, hey, maybe I should punch that in my calculator 3 times. But you could absolutely set it up like that. Just remember to actually do the number and cube the number, not just the units. It's a really, really common error. Any questions on that there? Questions on conversions, dimensional analysis? Again, when it says in chemistry, pretty much show your work, that's it. Yes, dimensional analysis, units, and for conversion factors. Any questions? All right, then we will continue on to the final subject here of chapter 2, dare I say, which is density. So we're going to talk about density. Density is a formula that represents the amount of matter there is in an object to its volume. Differences in density, for example, will determine, for example, whether or not an object will sink or float in water. If a substance is more dense than water, it will sink. If a substance is less dense than water, it will typically float. If you ever, typically speaking, in chemistry, need the density of liquid water, it is basically 1 gram per milliliter, or 1 gram per cubic centimeter. Remember that, as we saw earlier, 1 milliliter is 1 cubic centimeter. That is definitely something you should know. It is a value that does pop up a lot in chemistry, especially when you need density of liquid water. And a lot of times they don't just give it to you in the problem. They just kind of assume that you're going to use the 1 gram per milliliter. By the way, just a side note, density does change with temperature, but in the most cases, if you do need a density value of liquid water, 1 gram per milliliter is true. Now, water is an unusual substance. As you may know, the solid version of water is actually less dense than the liquid version of water. That is why our ice cubes float to the top of our beverages, right? Because it is less dense than its sort of liquid counterpart. And that has a lot to do, as we'll talk about in a later chapter, when water comes together in the solid state. What ends up happening is those water molecules, because of the strong hydrogen bonding that happens between them, they don't have enough energy to get really close to each other. So what happens is when water freezes, it creates a lot of really open space between the water molecules. And because of that, that actually lowers the density of water in the ice state or the solid state. Also why, right, if you've ever left like a can of soda or something in the freezer by accident too long, it starts to swell at the bottom, right? Because the water molecules start to freeze. They got to go somewhere, and they make the bottom of your can start to wobble and stuff like that. Yes, sir. Yeah, as I just mentioned, when it freezes, it creates a lot of open spaces between the different water molecules. So that increases its volume because there's a lot of empty space between the water molecules. Other questions? All right, so let's talk about density and the formula for density. Density is mass divided by volume. Oops. So if you want to calculate the density, it is mass divided by volume. That is the formula. And we can rearrange this formula if you need the volume. That is mass divided by density. Or if you need the mass of an object, that is the volume times the density. Those are 3 ways that you can rearrange this formula. Some people like to remember everybody's favorite place, the DMV. Triangle. Density is mass divided by volume. Volume is mass divided by density. And mass is volume times density in this case. And you can rearrange it. Typical units of density for solids and liquids, as it says on the bottom, are typically grams per milliliter or grams per cubic centimeter. Although we don't see too much of it in this class, but if you go to 1A, you will. Typically, units of gases, or density of gases, have units of grams per liter. So sometimes, a lot of times, gases are given in grams per liter. But I would say pretty much 100% of the time here in this class, if you're talking about density, those are going to be your 2 common units, grams per milliliter or grams per cubic centimeter, which, as we just mentioned a second ago, milliliter and a cubic centimeter, basically the same. Obviously, you could get a volume by simply just taking a reading. We could get something like a cubic centimeter by taking a length times a width times a height, as we've been talking about, of a solid, like you'll do next week. Again, centimeters times centimeters times centimeters will give you that cubic centimeter. So those are 2 very common, obviously, ways that we could get the volume of a liquid if we need to figure out its density. The units here for density will not cancel out, and you will end up with 2 units for density. And again, the number will stay with the grams part, and it's usually 1 milliliter or 1 cubic centimeter. That means, again, you could take a dimensional analysis approach when you're doing some density problems. if you are given the density. So if you are given the density of an object, and let's just say the density was 1.5 grams per milliliter, you can use that just like a regular conversion factor, and you could kind of flip it around the other way. And again, as I was saying earlier, take a dimensional analysis approach to the problem, and you may not even have to worry about the formula of D equals M over V or something like that. So again, you can kind of use it in that sense. Also, why, right, if you take a can of, say, Diet Coke and a can of regular Coke and you put them in water, will they both sink? Will they both float? One will do one and one will do the other. The one that will float is which one? The one that will float in the water will actually be the Diet Coke, right? The regular Coke will sink to the bottom. That's because regular Coke's got sugar. Diet Coke's got artificial sweetener. So it actually one will sink and one will actually float. All right, so let's take a look. So obviously in this case, we're looking for the density. So D is equal to M divided by V. In general, in chemistry, it's a really good idea to pull out the information from the problem. A lot of times, if you kind of pull out the information from the problem, you know some of the formulas. Oftentimes, it kind of points you in the right direction if you're not sure. So obviously here we have a volume that is 25.3 cubic centimeters. We do have a mass that's 21.7 grams. Obviously, that is everything we need. So in this case, all we have to do is plug it in. So 21.7 grams, 25.3 cubic centimeters. And that's going to get us 21.7 divided by 25.3. And going to get us a 0.8570751 grams per cubic centimeter. Clearly, you don't want to give all those numbers, but I just wrote it to illustrate. And a reminder again, it does not give your answer to the right number of sig figs. So we do need to look at our sig figs here. And we are dividing, which means that is 3 sig figs up on top. That is 3 on the bottom. And then we are looking at sig figs when we are dividing or multiplying. So our answer should end up over here at 3 significant figures and a 0.857 grams per cubic centimeter. Remember, the number stays with the grams part, and it is 1 cubic centimeter. Yes, sir. A 0.85. Oh, there is. There's my screen is dirty. Yeah, look at that. It doesn't look like a 1. So it is, thank you. Yeah, 857707. 85. I'll squeeze them in there. 7707. That means that we would actually round that up to 0.858. Thank you. Like totally had like a dirt on that. Other questions? All right, let's continue here. Now, we talked about a second ago 2 very common ways that we could get the volume of a solution. Obviously, there's type of glassware. You could just take a volume reading. If you have some type of solid that's sort of like a cube, you could do your length times your width times your height. Again, you can measure all those things in centimeters and you get your cubic centimeter volume. The third and very common way that we can get a volume of a solid is by displacement, volume by displacement. And volume by displacement is an idea that if you take a container that has a certain amount of liquid in it, like water, it will have an initial volume of where it's sitting. If you take a solid object, like our diver here, and you put them in the object, we will see that volume rise as a result of the solid object going in there. That is displacing the water volume, and that would be our final volume. So the volume of the object, or the person in this case, is basically the difference of the volume at the beginning and the final. So the volume of an object, when you do volume by displacement, is the final volume minus the initial volume. That is a very, very common way with density that we can determine a volume of a solid. You'll do that next week too. Toss it in a graduated cylinder, a stopper, and displace some water, and you'll figure out the volume of your stopper. So those are three, again, common ways that we could do that. So let's take a look here at a problem. So why don't you give it a go? A student fills a graduated cylinder with 25 milliliters of a liquid. She then immerses it in the solid in the liquid. The volume of the liquid goes to 33.9 milliliters. Solid has a mass of 63.5 grams. We are looking for what the density is. So take a few moments there and calculate it up and see what you get. Okay, so let's take a look at this. So basically what's happening here is we have a graduated cylinder, and it is initially filled with 25.0 milliliters. That is our initial volume. We're going to take this solid object here that has a mass of 63.5 grams, which is our mass, and we're going to drop it in there. And obviously, when that happens, we are going to see our volume rise with the object in there. And it's going to rise to 33.9 milliliters, which would be our final volume. So we are looking for the density, which is mass divided by volume. We obviously have the mass right off the bat given to us. We do need to find our volume through this displacement. So remember that the volume of this object is basically going to be the difference here between those two volumes. So the volume of the object is going to be our final volume minus our initial. So that's going to be 33.9 milliliters minus 25 milliliters. And that's going to give us, I believe, an 8.9 milliliters. And that is the volume of the object, which is also, again, sort of our last thing missing here. And now if we put our density in there, we got our 63.5 grams. We have our volume of 8.9. And that's going to give us a density of 7.1 grams per milliliter. Once again, number stays with the grams per 1 milliliter. In terms of significant figures, we want to look at our last calculation. That is 3 significant figures. That is 2 significant figures. We are dividing here, so we are looking at sig figs, and we should end up with 2. But really, our 2 significant figures is based off of this calculation, where we went to decimal places. And in this case, it was 1 decimal place. 1 decimal place gave us 1 decimal place here, but did give us 2 significant figures. So really, it is based off of that calculation. And you do want to make sure you go back and look at that calculation, as obviously it could affect the end calculation as well. Yeah. Any questions on that one there? Okay. So here's a table from your book of some common densities. As I mentioned before, that's pretty much one you definitely should know, which is the density of liquid water. Again, as you can see there, ice is actually less dense than it, and it's more like 0.9 instead of 1 gram per milliliter. Here's another table, some common sort of liquids as well, and densities of those guys. Let's take a look at one more example here. A student needs 150 cubic centimeters of salt for an experiment. The density of the salt is 2.16 grams per cubic centimeter. We want to know how many 1 pound boxes of salt should they bring to class, I suppose. 1 pound, 453.6 grams that you should know. All right, so take a few moments there, calculate it, and see how many 1 pound boxes we're looking for here. Okay, so let's take a look. So obviously we can pull out the information here. 150 cubic centimeters is a volume. And we obviously have the density here, 2.16 grams per cubic centimeter. So obviously here you could look at the density equation. If you weren't sure, you got density, you got volume. Mass seems like a really good place to start since that's the only thing you don't have. And again, if you rearrange this correctly, mass is volume times density. Now, as I mentioned before, some of the benefits of perhaps dimensional analysis is you might not even have to worry about the formula or rearranging the formula if you're not really comfortable or confident that you're going to do it correctly. You can take a dimensional analysis approach here since we were given the density. And because we were given the density, we really can use the density here as a conversion factor, just like we did previously. We could use it either way. And again, if we take sort of that dimensional analysis approach, we don't even really have to worry too much about that actual formula at all. We could just kind of do a dimensional analysis setup. We could take our 150 cubic centimeters, and I want to get rid of cubic centimeters. So just like a normal sort of deal, I'm going to use this guy. Cubic centimeters are going to cancel as I multiply and divide. I don't even have to think about, math-wise, should I be dividing? Should I be multiplying? I could just do it this way. And we will end up with, obviously, 324 grams. We would obviously end up with the same thing if you rearranged it. But again, if for some reason you couldn't figure out or remember the formula or something like that, again, kind of sometimes taking a dimensional analysis approach, as long as you can figure out what units you got to kind of get rid of and what units you need to kind of keep, it oftentimes will just kind of walk you through almost the formula and rearranging it for you. With that being said, we do need 324 grams of salt, which, by the way, significant figure-wise from this calculation, that is 2 sig figs, that is 3 sig figs. Really, if we were going to give an answer for grams, we would need about 320 grams. But the question actually is asking how many 1 pound boxes do you need? And since a pound is 453.6 grams, that is less than a pound. So you need at least one 1 pound box. So it brings up two important things about problems. Make sure you actually answer the question that's being asked. Yeah, so sometimes people answer questions that aren't really being asked. So you want to make sure that you read it and make sure that you do answer the correct question. Any question on density there? That is chapter 2, I believe. 3 is actually a fairly short chapter. It's not very long at all. So we're going to get a little bit into chapter 3. We're going to talk about matter, and we're going to talk about some of the different states of matter. We're going to talk about substances and mixtures in this chapter. But when we talk about matter, as we talked about the other chapter, it's basically anything that occupies space and takes up mass. There's really 3 states of matter that we very commonly come across, and that is the solid state of matter, which typically has things packed in very tight to one another. They don't have a lot of energy, so they lack a lot of movement and stuff like that. They're usually, again, very rigid because of that. We also have the liquid state, where things are still relatively close to one another. The difference is they do have a little bit more energy in the state. So they do have energy to sort of pass one another. That's why when we take a liquid, right, it pours rather than like a solid that just kind of clumps out as they're all packed into each other pretty tightly. We also have the gas state. And in the gas state, that is the state where everybody is basically completely broken apart. They're flying around. They have a lot of energy. And as we'll talk about later on, as they're moving around and flying, they're colliding with the walls. That's what's going to cause pressure that we associate with gases. So we'll talk about that, obviously, when we get to the gas chapter officially. So these are the 3 very common states of matter. Some other things that we'll talk about in some other chapters as well that relates to this is the transition as we go from one state to the next. So the process as we go from solid to liquid That is the process of melting. Like if you take an ice cube out, it starts to melt. It makes liquid water. If you feel sad about your liquid water that melted, you could then take it, put it back in the freezer, and go from liquid back to solid, which is the process of freezing. As you go from liquid to gas, that is the process of evaporation or vaporization. As you go from gas back to liquid, that is the process of condensation. Steam molecules, like when you take a shower, hits the cold mirror, a lot of water on the mirror, right? It becomes liquid water back. We also can go from solid directly to gas, skipping the whole liquid cleanup, and that is what is known as sublimation. A common example of sublimation you may be familiar with is dry ice, and dry ice goes from solid directly to gas under normal conditions, skips that whole, like I said, kind of liquid cleanup phase. By the way, dry ice is not water. Yeah, dry ice is carbon dioxide. Super cold. Yeah, if you touch it. And there's also a transition that you could go from gas back to solid. Again, skipping the liquid cleanup there. That is what is known as deposition. So another sort of thing that we'll talk about in chapter 10, which is about energy. The energy relationship here is there's a certain amount of energy process that occurs as you go from one state to the next. As you go from solid to liquid to gas, do you think you need to put energy in to do that, or do you have to take energy out? Yeah, you do have to put energy in to do that. So if you just think about the ice cube, when you take it out of the freezer, it absorbs all the energy from the surroundings as heat moves from hot to cold. So the ice is much colder. So the energy from the air basically goes in there and starts to melt it. And energy has to be put in or absorbed. And one of the words that's really important in chemistry, when we talk about a process that involves energy being absorbed, that is what is known as an endothermic process. So if you hear somebody say endothermic, that is a process where energy is being absorbed. So the ice cube, it's endothermic for the ice cube. It's absorbing energy as it starts to melt. When you boil water to make pasta, right, you put fire underneath it, right? So it absorbs all that heat and energy and it starts to boil. The opposite is true. If we go from gas to liquid to solid, we do have to remove energy in that process. So energy is being released in that process. And that is what is known as a exothermic process. So endothermic, we absorb energy. Exothermic, we release energy. So if you think about gas molecules that are flying around really fast with a lot of energy, if they release their energy, they're going to start to slow down. And what happens is when they collide with other gas molecules, they no longer have enough energy to escape each other. And they kind of clump together and drop into the liquid state. You continue to remove energy, they then get closer to each other. They don't have enough energy to pass each other anymore. And they lock themselves into the solid state at that point. So going from solid to liquid to gas is an endothermic process. Going in the opposite direction, gas to liquid to solid, is an exothermic process. Does melting and freezing occur at the same temperature or different temperatures? Yeah, melting and freezing does occur at the same temperature. And for water, for example, that was 0 degrees Celsius. For water is where that occurs. And the same thing with evaporation and condensation. It happens at the same temperature, and for water, that is 100 degrees Celsius. For where it freezes and melts, that's the normal melting point, freezing point for a substance. Where it boils, it is the normal boiling point, or it does that transition. At exactly 0 degrees Celsius, for example, if you take water, you basically have both phases happening at the same time. You have some liquid, you have some solid happening exactly at 0 degrees, like ice crystals. You got some ice crystals. It's not until you get a little bit above 0 degrees that you fully sort of transition into liquid water, not until below 0 degrees that you transition into ice. And the same thing at liquid to gas and gas back to liquid at exactly, say, 100 degrees for water. You have both phases happening at the same time. It takes, as we will see in chapter 10, it takes a lot more energy to do the transition as you go from liquid to gas than it does as you go from solid to liquid. Because as you go from liquid to gas, everybody's completely breaking apart. So it takes a lot more energy to get them apart. Liquid to solid, they are still relatively close to each other. Yes, sir. Uh, so we won't talk too much about it in this class, but in like 1A and stuff like that, or you will talk a little bit about it. But uh, things like pressure and temperature sort of relationships can affect boiling points and melting points and stuff like that. And also having other things in a solvent or a solution can affect things like boiling points and freezing point. Like for example, freezing point elevation, boiling point, boiling point elevation, freezing point depression uh, can be affected by things in it. For example, if you have a traditional car or a car with antifreeze, that's what antifreeze does in your car. It has stuff in it with water, and with that stuff in it, ethylene glycol, will raise the boiling point of water and lower the freezing point of water. So if you live in a really hot area, your car won't overboil. And if you live in a really cold area, your water and everything in your car won't freeze. And because it has other stuff in it, it affects things like boiling points and melting points and freezing points of substances. All right. So obviously we just sort of touched upon this, but officially matter again is the stuff that the universe is composed of. It basically has two sort of characteristics. It has mass and occupies space. As we just saw there, solid is has a definite shape and it's very difficult to change it. They're very rigid. Obviously, something like the desk here, you can't just easily fold it up on itself or anything like that. So it's very rigid, very hard. Typically, particles are very close to one another in the solid state. Obviously, water, like we talked about in the ice state, which is its solid state, is an exception to that. But most things in their solid state, they're usually more dense than in their liquid state, and that's because they could get really close to one another. Liquid, on the other hand, does not have a definite shape, but does have a definite volume, and it will really take the shape of whatever container you put it in. So what that means is if I had 10 milliliters of water and I put it in a water bottle, it would take the shape of the water bottle. If I took the 10 milliliters of water and poured it into the trash can in the front of the room, it would take the shape of the trash can. It has a definite volume because if I start with 10 milliliters of water, no matter what container I move it to, it should still be 10 milliliters of water unless you're a klutz and you spill it on the floor. But ideally, if you transfer it correctly without dropping anything, you should have the same volume no matter where you put it. But if you put it in one of those silly straws, right, it's going to take kind of the shape of the silly straw as it goes around in circles. The gas phase, air obviously is an example of a gas. Hydrogen, nitrogen, oxygen, which are components, takes the shape of its container and fills it uniformly. In most cases, especially as we'll talk about in the gas chapter, we do assume gases to be what are sometimes referred to as ideal gases. Ideal gases are basically, they're just flying around in the container. It doesn't matter what other gases are in there with them. Under normal conditions, we just kind of assume they're in there by themselves. The volume of the gas is not really important in an ideal situation. What's actually important is the container. So we oftentimes talk about gases in terms of the volume of the container because they are constantly flying around. They are uniformly sort of filling the container as they are moving around in the container in the gas state. Obviously, a few of our liquids in some different shapes. Here again is our three states of water. And this also illustrates what I was talking about earlier. Again, our water in the ice state. And as you can see here, because of the hydrogen bonding, this is all open areas between the different water molecules. They cannot get themselves super close to one another because they don't have enough energy and because they're being held off by a really strong sort of hydrogen bonding between them. And because of that, as we just talked about, mass over volume for density increases the volume, and that decreases the density of ice versus liquid water. Where oddly in the liquid state, you can see the water molecules, because they actually possess a little bit more energy, they could actually get themselves a little bit closer to one another, and they actually pack themselves in there a little bit more than they do in the ice state. And like I said, that is a very unusual sort of characteristic. Most things are sort of the reverse. Most things in their solid state, they're more dense than in their liquid state. And obviously in the gas state, we have just water molecules flying around. Now, the state of a given substance really depends on the attractive forces between the molecules. The stronger the attractive force is, the more rigid the matter will be. So, for example, when we have molecules, the same molecules, they are basically held together by forces. And as we'll talk about in a later chapter, these forces are what are known as intermolecular forces. So intermolecular forces are really the forces that hold two molecules together, like two water molecules together, a bunch of water molecules together, a bunch of other methane molecules together. And all intermolecular forces we'll talk about in a later chapter revolve around a really important concept in chemistry, which is opposites attract. So things that have different charges, a positive thing and a negative thing, will be attracted to one another. Much like in life, right? Two negative people, that's just not a fun day, right? Two positive people, that's too much joy, right? So they always say you want to find somebody that balances you out, right? A positive, negative, and they are attracted to each other. So the positive side of one molecule is attracted to the negative side of another, and that's the intermolecular force that holds, for example, a bunch of water molecules together. That intermolecular force, for example, for water is hydrogen bonding, what's known as hydrogen bonding. And if you have a really strong force that holds, say, like a bunch of these molecules, the same molecules together, it is most likely that guy is going to be found in the solid state because they're not going to be, it's going to take a lot of energy to kind of break them apart. If you have something that is held together molecule to molecule by a very weak force, and we'll learn about that weak force in a later chapter, is what's known as dispersion forces. It is what, for example, when you light a Bunsen burner, which you will do next week, and you open up the gas, that is methane that's coming out. That's methane gas that's coming out. Methane and another methane molecule and a bunch of methane molecules, they are held together by super weak forces. So weak that they are like, I'm just going to be in the gas phase. I don't want to stay together. We're just going to kind of break apart and be in the gas phase. And there are certain things that are held together by very weak intermolecular forces that are normally found as gases, like methane. There's even things that are liquids, for example, that are still held together by relatively weak forces that it doesn't take a lot of convincing for them to go into the gas phase. Those are things that are known as being volatile. You take the bottle of liquid, you open it up, and it vaporizes, basically. It just goes into vapor. A lot of organic molecules are like that. So if you ever take organic chemistry, they stick you in a fume hood when you use those things because very commonly those things can go into the gas phase very easily. And the second bad thing about those things is they're oftentimes flammable. So you don't want to open flame near them either because they could catch on fire. But the idea behind solid, liquid, and gas is if you have something that's held together by a really strong intermolecular force, it is most likely going to be a solid or a liquid under normal conditions, and it will probably have a very high melting point and boiling point. If you have something that's held together by a very weak sort of intermolecular force, it will probably be more of a gas at normal conditions and will be basically have very low melting point and freezing point as well. Any questions on that there? And we'll talk more about those sort of forces in a later chapter. All right. Actually, I think we're going to lay it up there for today, I think.